Hello, I'm Mr. McBrien. This is TEJ20, the Conga line principle. So today we're going to attack a few misconceptions that many people have about circuits. To address these, we're going to discuss conductivity in metals. We're going to discuss the effect that resistors have on current and gain. And we're going to talk about current before and after a resistor, something I call the Conga line principle. So let's address a few ideas that people have about circuits, that a few misunderstandings about the way that we get energy from current, the way that electrons move through a simple circuit. Many people misunderstand these things, and we don't want to be those kind of people, because if we are, we won't really understand what's going on in the circuits we design. So today we're going to try to unlearn some bad ideas about electricity, some things that you may or may not have carried with you as you've learned more and more about electricity and its role in circuits. So some misconceptions that many people have. One thing that people often say about circuits is that circuits convert electrons into energy. And this is absolutely untrue. Another thing that people think about circuits is that they consume electrons. Again, completely untrue. Electrons aren't destroyed in circuits. Circuits don't use up electrons. We have the same number of electrons before and after our circuit functions. So that leads us to a question. Where do we get the energy from if it's not from the consumption of electrons? And the easiest way to explain this is to describe electrons in a circuit like rocks in a ladder. So if we consider a rock at the top of a ladder, it has energy. We call it potential energy. It has energy available to us. And we can use that energy to do things, to do work. For example, we can use the energy that a rock has at the top of a ladder to break a toe. Not maybe the most pleasant application, but we can do it. But here's where the analogy is useful for us with regards to a circuit. When we're done breaking the toe with the rock has moved from the top of the ladder down to the ground. It's lost that potential energy it had. It's lost that energy. But the thing is, the rock isn't used up. It's still a rock, right? And circuits are like this. So circuits are like this. An electron gives up its energy to do something, but it's still an electron. So how do we get then that energy from the electrons? Well, like the rock at the top of the ladder, electrons have potential energy provided by our potential source, usually a battery in our case. And any electrons that are at the negative terminal of the battery, well, those electrons have lots of potential energy. Any electrons that are located at the positive terminal of the battery have lost that potential energy. They have zero potential energy. So the electrons give up the energy as they move through the circuit. And this is the energy that powers the devices that we make as part of our circuits. So what's all this mean? It means electrons are not consumed by our circuits. Electrons move from the negative terminal to the positive terminal as the circuit functions, but they're not consumed. Instead, they lose energy as they go. Now here's another misconception that many people have about our circuits. When they describe what happens when an electron goes through a resistor, they talk about the electrons starting out fast and slowing down as they go through the resistor. And in fact, that's completely untrue. Electrons all move at the same speed in a simple circuit. Now that might make you a little bit uncomfortable. Didn't I tell you that resistors slow down the speed of electrons? Didn't we do experiments that proved this was the case? In fact, we did. And resistors do slow down the speed of electrons. Okay? But resistors slow down the electron flow all the way throughout the circuit. If they didn't, think about what we would have. So we now know that electrons don't get consumed in a circuit. We know all of the electrons that start at the battery have to go back to the battery, right? So if the electrons moved quickly towards the resistor and then slowed down afterwards, well, they all bunch up like cars in a traffic jam. And you'd have electrons accumulating in your circuit. And the fact of the matter is that electrons only accumulate in very specific, very special kinds of circuits that we'll in fact discuss later in this course. But our simple series circuits have no accumulation of electrons anywhere. And to understand how this works and why it works, we have to dig deeper into the way that conductivity works in materials like metal. So this is a little cartoon of a lot of copper atoms that might be arranged into a wire. And conductivity in these metals, copper of course being a metal, occurs by electrons transferring to one of these atoms. But as soon as an electron transfers to a given atom, another electron moves off of that atom to an adjacent atom. And this process continues with electrons moving through the conductive material until eventually an electron can exit the last copper atom at the end of our wire and go back to our battery. Now, if we can get that concept down, if we can understand this, that current moves, electrons move by jumping from one atom to the next, and that each electron needs an electron to move out of the way to make space for it. As soon as we understand this idea of one electron leaving and the next one taking its place, we can understand how charge could never build up in our circuit. We can't accumulate large amounts of electricity anywhere in our simple series circuit. But all this means that in order for an electron to go from the battery onto our wire, we need a different electron to move off of our wire onto the positive terminal of the battery. And all of conductivity works in this way. So I like to call this the Conga line principle, where electrons all move essentially touching each other, and one electron has to move forward so that the other one can take its place, and that one has to move forward so that the other one can take its place, and so on and so on. So what does all this mean? It means that the current in a simple circuit is the same at any point. No part of our Conga line can go faster than any other part of the Conga line, or we will see an accumulation of electrons, which is something that can't occur. So if we want to go back to our schematics and look at this in terms of diagrams that we are used to, we can say that the overall current in our circuit, I, leaving the battery, is equal to the current before resistor 1, the current after resistor 1, and if I want to add this in, that's also equal to the current after resistor 2 that goes back into the battery. So in mathematical terms, the overall current of the circuit is equal to the current in node 1, which is equal to the current in node 2, and equal to the current in node 3. In fact, the current is the same all the way through. And if we were to put an ammeter in each of these locations, we would see the same value for each one. Okay, to summarize then, energy in circuits comes from moving electrons from a high energy location, the negative terminal of the battery, to a low energy location, the positive terminal. Circuits don't consume electrons. When we're done using our circuit, we still have the same number of electrons as we had when we started. And an extremely important idea, electrons do not move quickly to a resistor and then slow down after they've moved through it. In fact, the Conga line principle applies. And what this means is that in a simple circuit, current is the same at any point. So for your homework, what I'd like you to do is design an experiment inside the PhET simulator to demonstrate the Conga line principle. So build a series circuit with several resistors. Put an ammeter before and after each resistor. Then when you're ready, flip the switch, measure the current at each node, and demonstrate that it's always the same. Okay, so go ahead and have fun. Thanks very much and have a great night. Hello, I'm Mr. McBrien. This is TEJ20, the Conga line principle.